Yeah, thank you all. Good afternoon. So I'm going to talk about superconductivity. I thought back and forth, quantum anomalous Hall or superconductivity, but I correctly surmise there will be many talks on quantum anomalous Hall by this time, and not that many on superconductivity. So this is a list of, all the recent superconductors two-dimensional system. On the left side are the twisted system, magic angle system, and for a while the myth was that you must have Moiré is essential for superconductivity. Well, then Andrea Young wrote this paper, and now we know that Moiré is not essential at all. Basically, superconductivity is everywhere in 2D system, okay? You just have to do the measurements and you'll see superconductivity, okay? Now, you may wonder why, by the way, if your paper is not listed here, then write a very angry note to Yang Zi Cho, okay? He made this list for me, okay? I asked him to make an exhaustive list. I apologize if your thing is not here. Now, you may say, why am I showing it? That's because I have been in the subject of two-dimensional physics for a very long time, longer than most of you have been around. And the dream was superconductivity, okay? You know that 2D semiconductors go back to 1965, when in IBM, through Shubnikov-Dehaas measurement, people showed that the silicon MOSFET is two-dimensional system. And there are several 100,000 papers in the subject, in 2D subject. Silicon, gallium arsenide, indium arsenide, aluminum arsenide, graphene. None of them ever showed superconductivity until 2018. Not because of lack of predictions, theorists predict things all the time, and there'll be often predictions, oh, silicon MOSFET will go superconducting at 100 millikelvin. And immediately in Bell Labs, David Bishop and Bob Dines will cool things down, nothing. Nobody saw superconductivity, but this system manifested quantum Hall effect, fractional quantum Hall effect, Wigner crystallization, strong localization, weak localization, 2D plasmons, ferromagnetism. Almost all condensed matter textbook properties were seen, and quantum Hall effect and fractional quantum Hall effect and weak localization, 3 properties were discovered in 2D systems, but no superconductivity. Perhaps the most important condensed matter phenomenon until now. Now, with these new systems, you cannot avoid superconductivity. Physics is just magical, right? I mean, something that didn't happen is now like commonplace. And to me, it's like, very, very surprising, since I have spent most of my life doing 2D without any superconductivity. Well, this is the original experiments. I think I have the original one. This is Pablo's original experiment. This was shown a couple of times already in this conference. This is twisted bilayer graphene, and magic angle is not necessary. Well, there is no magic angle, but magic angle is not necessary, just some twist, and then you get superconductivity and some commensurate filling, and you get these insulating phases, which originally was called MOT, but these are just insulators, not very strong insulators. They're arising from symmetry breaking. This is Andrea's data, which I think is the first confirmation of the MIT experiments. This is superconductivity, as you can see. Superconductivity. This is Efetobs. He's in the audience also. This was presented in a KITP meeting, I think, I don't remember when, 2019, 2020. And when I saw this, my first feeling was, look at it. It's all superconductivity. It will be all superconductivity. Some other phase is coming in, preventing superconductivity from developing. It must be phonons, because it's all superconductor everywhere, if the strongly correlated states did not exist. And so now, of course, superconductivity is common. You just see, we know that Moiré is not essential. So if Moiré is not essential, if it's happening in regular graphene, then phonons have to be taken very seriously, because I'm going to make up a number. I would say 99.999% of known superconductors are phonon mediated. But 99.999% of theory papers are electron-electron interaction in the superconductor. So we have this dichotomy. So, but on the other hand, on a more serious tone, phonons must be ruled out. Those who believe phonons may be the cause do not need an excuse to work on phonons. You have to first rule out that phonons are not the cause, and so. But the fact, if you saw it only in Moiré, then you'd say, Moiré has all these other interesting properties. Like the reason we believe in high TC, it may not be phonons, but if you're seeing in regular tri-layer, bilayer, 4-layer, 5-layer graphene, you have to take phonons seriously. Now there is another reason it may not be electron-electron interaction. By the way, I have nothing against electron-electron interaction. Most of my work is on electron-electron interaction. Electron-electron interaction is my friend, okay? So do not think that I am against electron-electron interaction, but I'm very pro-reality, okay? Whatever is correct, So, but there's these experiments, and I'm sorry, I did not put the names of the authors, but one is Andreas, one is GLE's from Brown, and there's a third one, maybe even Bemis. What they did, precisely to look at this issue of whether it's electron-electron phonon, they put a gate very close to this graphene, TBLG, and the idea was, if you put a gate, you can screen the electron-electron interaction. So if it's electron-electron interaction, superconductivity will disappear, or at least will be suppressed. If it's electron phonon, not much would happen. Actually, superconductivity should be slightly enhanced, because you'll be suppressing the so-called mu star effect, which I'll talk about later, electron-electron interaction. And that's what happened in these experiments, okay? Again, I'm not going to describe any of the experiments in details, but I'll show you some experimental data, mostly to keep Andrea Young happy. You don't want to make him unhappy, okay? So, because each experiment will take a day to kind of describe what's going on. But you can see here is the device where they put the gate 38 nanometer, 380 angstrom from the device. Superconductivity is there, and some kind of insulating phase is there also. Same experiment, they put the gate just 7.5 nanometer, insulating phases are all gone, superconductivity is still there. And this was some kind of evidence, it was thought to be direct evidence that it's unlikely to be electron-electron interaction. It doesn't prove that, but it is there, okay? So this is, again, a table for what I just showed you before. By the way, several new things were discussed in this conference, and there has been a huge number of like 5 or 6 postings this week, probably connected to this conference. They are not in this list. And again, you can see, twisted bilayer graphene plus tungsten diselenide. Stefan talked about it just in the morning. Twisted trilayer graphene. Then the more, just larger number, twisted bilayer, double bilayer graphene plus tungsten diselenide, Bernal bilayer plus a TMD material, rhombohedral trilayer. And now this is the main thing I'll talk about later. All of them have been seen. This is the thing, and all of them, some of them probably only phonons we think are the relevant things. Some of them definitely isospin fluctuation may be playing a role. And I'm going to kind of try to give a broad view. As theorists, we want generic and general application, universal. We are always looking for universality. Now, nature may not be universal. Maybe each sample has its own mechanism for superconductivity. That cannot be ruled out. It's unlikely, but logically it cannot be ruled out. So it's quite possible that some of them are phonons, some of them are something else, okay? So one should keep that in mind, okay? One should be very modest and humble approaching it. You have to look at it. We did lots of papers on it, okay? And the reason is there are lots of experiments. Each experiment comes, you immediately write 2 papers. One saying it's phonons, one saying it's isospin fluctuation, okay? So that if Senthil writes a paper, we have already staked a claim. Slightly facetious, okay? I'm going to talk about some of this work, okay? Here is Andrea's experiment. Andrea's work was very influential in our thinking on it, and I'm not saying it to flatter him. I'm saying this because it's the truth, and he knows we talked a lot about it. And this is superconductivity rhombohedral trilayer graphene. You can see this figure has been shown, and this is one thing we want to understand. And then superconductivity in Bernal bilayer graphene. Again, you can see superconductivity. The details I'm not going to talk about, the experimental papers. We can discuss it later on. But I'm just showing you that these are some of the experiments theorists have to understand. Again, as I said, the most obvious candidate mechanism for superconductivity is always electron-phonon interaction, because most superconductors are electron-phonon interaction. Essentially, all non-superconductors are phonon-mediated. Some exceptions that is established are, for example, helium-3. It's not a superconductor, it's a superfluid. It's triplet, and that, of course, is not electron-phonon. Now, in regular graphene, electron-phonon interaction is very weak. And we estimate at TC it's going to be less than 1 millikelvin. So in graphene, you don't see anything. But there were already ideas that if you can dope graphene, and Philip Kim tried that, to very high density, to reach its Van Hove singularity, at the Brillouin boundary, there could be superconductivity. And I think this was Efetov's PhD thesis. It turned out that you cannot really dope graphene to such large density, but they did some beautiful electron-phonon interaction scattering work. Through this effort, they could go to very high density, not quite. So the idea has been around that maybe graphene would be superconductor if you can reach Van Hove singularity. But because of flat band in Moiré system, effective electron-phonon coupling is enhanced, and that could lead to superconductivity over Kelvin. These are things I'm going to explain. And the most important thing, which you have to really struggle with the referees, some referees say, oh, if it's phonon, it must be S-wave. That's correct for 3D metals because there is no other symmetry, just a spin. But if you have many other symmetries, that's not true because overall you want the whole wave function to be antisymmetric. If you have many other quantum numbers, you can have any symmetry order parameter that you want. And I'm going to show you, and this is something Feng Cheng and Wu and I worked out. So phonons are therefore the leading candidate. That doesn't mean that it's phonons, but you have to work out the details. So let me start by telling you that because of these other symmetries that are present in the system, valley, pseudospin, layer, depending on what you have, you can work out the symmetries, and I'm not going to go into the details. This is more or less well established that with pure acoustic phonons, you can SP, DS scattering, pairing. With plus minus K optical phonons, you can get S and D pairing. And with gamma optical phonons, you can get S and F pairing. And you can work out the symmetries for any phonon that you like. What are the possible superconducting order parameters? It's by no means S. And then you have to do precise calculation to see what it is. The critical temperature, if you just use ordinary BCS theory, is this famous formula, exponential -1 over lambda BCS. This is why superconductivity took 50 years to explain. It's an essential singularity. Perturbation theory doesn't work. At lambda BCS, the theory is meaningless when it's 0. And in 3D system, this EC is typically a phonon energy scale, theta dBi or something. But actually, if you do the theory right, the real energy scale is here, whichever energy scale is smaller, phonon or electron. For many of the systems you are talking about, this is really more like a Fermi energy. But this lambda BCS is a product of density of states and the bare phonon coupling. And if you have a Van Hove singularity, density of state is going to be very, very large. So this is then enhanced even if G0 is small. And this is really the main physics. And when you estimate it, even at the BCS level, you find that this number is of the order of 1. And this was our first realization in this paper, which we presented in a conference here when, 5 years ago, some of you were there, I know, okay? And pointing out that phonons could be the mechanism here because of this argument. So, and you can get phonon-mediated triplet pairing because of the beauty of this additional symmetry. Okay? So the theory then is you have to put in the correct band structure, correct symmetry properties, but the theory is the standard Eliashberg theory, although you do not solve the full Eliashberg. Mu star part, we do some approximation. So you write down the linearized gap equation in each symmetry channel, and this is almost textbook stuff. And then you solve the BCS equation self-consistently. This is the result for twisted bilayer graphene, Moiré. And as you can see, as I already told you, that it's S and F are allowed, and you can see that S and F are degenerate. Symmetry says they're degenerate, and their TC is very high. P and D are also degenerate, but TC is small. So our conclusion is that what you're seeing could be S or F superconductivity in twisted bilayer graphene. And in these papers, they're 5 years old, we worked this out completely, the symmetry properties, and this is, again, not full Eliashberg. Mu star is approximated by hand, but it's a genuine self-consistent solution of BCS theory with the full band structure of twisted bilayer graphene, okay? Then came the Bernal bilayer graphene. This was very exciting for us. And so we did a more complete theory here. And what we did is, so the basic thing, you must use the correct band structure because the Van Hove singularity is very important. One objection, mostly from Pablo, was that, look, Van Hove singularity is 1 point, but TC is finite over some range of density. So it cannot be just Van Hove plus graphene. I mean, it's a genuine objection. I wasn't sure if that's true or not. I had this suspicion that if you do the calculation correctly, it's an integral equation, maybe the effect spreads around Van Hove, and when you do the theory, that's what we found. Here is the various Van Hove points. These are all for different displacement field. By the way, this displacement field is an amazing thing in all these 2D systems. This is what gallium arsenide, silicon, all those older systems did not have. This magic of displacement field allows you to do what I call Van Hove engineering. You can move around the Van Hove singularity and make your coupling for anything, electron, 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 phonon, whatever you want. It's something it took me a long time to appreciate the importance of displacement field. I always thought of it as a nuisance, displacement field. Displacement is the kind of language Maxwell used. It's just cannot be very relevant for quantum physics, but it's something experimentalists knew, that you change that and you see all kind of magical things. And only recently I understood how important it is in the context of, so for various displacement field you get, but the main point is that you get finite TC superconductivity or some range of density. Of course it peaks at wherever the Vanus singularity is. And I would say the agreement with experiment is about as good as you expect, given the complications of the system, given the band structure is not exactly known. In these calculations, we included the mu star effect. Mu star effect, if you do not know what it is, electron-phonon interaction creates an effective electron-electron attraction. The phonons, the interaction mediates to the boson, but electrons and electrons directly repel each other. So if that repulsion is larger than the attraction due to phonon-mediated interaction, you are going to get superconductivity. And there's a very famous example for that, copper. Copper would not go superconducting even if you go to 0 temperature. This is not very well known, because there the mu star, the repulsion due to electrons themselves, is larger than the attraction. So you have to include that at some level of approximation. It's a very difficult problem to solve because electron-electron interaction is non-perturbative, and typically the effect is called mu star, which effective lambda becomes lambda minus mu star, where mu star is the Coulomb repulsion. And we included it in doing random RPA in some static screening. That is the best one can do, and some improvement is necessary along this line. And every time we think that we're going to solve full Elias-Berg doing dynamical screening, a new experiment comes out. This is very difficult doing that. It can be done, but it's numerically very intensive. So the best that can be done, and this is what we did. And our agreement with experiment is pretty good. Okay. Now let me go to Trilayer graphene. Again, it's Andrea's work here in Santa Barbara. Again, the band structure is highly tunable by displacement field. There are all kinds of Stoner instabilities, because remember, those Van Hove singularities also give rise to electron-electron interaction-induced flavor polarization transition, right? So you have to take everything into account, and we took into account electron-phonon coupling, ferromagnetic spin fluctuation, and of course you have to use full band structure. I have to overcome my fear of band structure to do these theories, meaning, all my life I have worked with J-LEM and electron gas. That's what many body theory people do, okay? Either use a Hubbard model, a simple model, or use electron gas. But here band structure is absolutely essential. You're not going to get anything because the Van Hove singularity is the physics of Van Hove singularity. Everything here is physics of Van Hove singularity, okay? So here is our density of states. These two are taken from the experiment. Their band density of state calculation, this is our own density of state calculation. See, we have experimental agreement, okay? It agrees the experimental paper, of course it should. Both are, it just shows the experimental did the band structure calculation correctly, okay? So then we use this to do the same calculation that I told you, and we use the actual coupling for graphene. We are not fooling at the coupling, we are not adjusting the coupling, we are taking the actual coupling in graphene, but we are using the correct Van Hove singularity physics. And then you have to take into account the fact that there could be ferromagnetic transition and so on. And there are various caveats you can put. If superconductivity coexistence is ferromagnetism, then it must be phonons, because then you do not have any fluctuations coming from spin. If it's near the ferromagnetic transition, then it's possible that paramagnetic fluctuations are causing, okay? But phonons will still give you isosuperconductivity. So some details are still kind of open, but let me show you the result. This is almost like an Elias-Berg solution. And I'm showing you the grid over which we did the integral equation solution, and the results do not change much. Actually, finally, we went to a 1,000 by 1,000 grid. I did not bring those results. But the main point is that things have converged. This is a very big issue when you do Elias-Berg. And TC is finite far from Van Hove singularity. And it's of the order of, a Kelvin, which is the best one can kind of do under the circumstances. And again, the conclusion I told you that TC of the order of 1 Kelvin is possible. For electron-phonon interaction, again, electron-phonon interaction is what it is accepted number for graphene, which agrees with the experiment of Efetov and Kim for monolayer graphene resistivity, okay? So you can call this a first principles calculation. So I would say this is as good a calculation predicting, post-dicting TC as it is for aluminum or lead in three-dimensional metals, okay? This is the best one can do under the circumstances, okay? All right, so what about, we have a long paper where we give this thing, so let me just show you. This is Bernal. This is the density of states for each system. So this is where band structure comes in for different displacement field, as you can see. Here is no, this is a Fermi velocity. Sorry, this is we're calling, which is the Fermi velocity. And here is the band density of states. And here is, this is the density of states. This is the Fermi velocity, sorry. And this is TC calculated. The same calculation for 3 different materials. Note one thing, that all of these systems have finite TC. And the TC is of some order, and there is this asymmetry. On the electron side, TC is somewhat higher, hole side somewhat lower. All these details depend on the band structure in our calculation. These calculations have no adjustable parameter. It's just whatever, the band structure is standard. This is a Magnol type band structure. Well, very recently, like this week, Jihan extended that because of experiments from MIT and other places, tetralayer, pentalayer, hexalayer graphene, all with no moire. Very similar calculation is unpublished. And again, you can see graphene, for all I know, 737 layers of graphene will be superconducting with some TC. So it's possible that what Volovic was saying, that, that graphene, some graphene is room temperature superconductor, is possible. I mean, it's just, we are going to go actually up to 10 layers. Okay, we're going to be ahead of the experimentalists. These systems are very difficult to make, as you know, they're very fragile. Not many people can make these systems. I mean, so, but all of them should be superconducting. Okay, and actually all of them have already been seen to be superconducting. Now, last 10 minutes, I will talk about the title of my talk, which is, TMD. And this has a sad story. In some conference, actually happened in several conferences, I very boldly predicted, after talking about graphene superconductivity, that I predict in tungsten diselenide nobody will ever see superconductivity. Okay. And the advantage of prediction is that, when your prediction turns out to be incorrect, you get to write more papers. Okay. So, and the reason I said it is very simple. If you know anything about tungsten diselenide electron phonon coupling from DFT calculation, it's extremely weak, weaker than graphene. It's very weak. Nobody was talking about twisted TMD in those days to create Vanov singularities and so on. So I looked at the coupling constant. I said, this is a microkelvin TC. So it's never going to happen. It's just in tungsten diselenide. Other TMDs have much higher electron phonon coupling, and most of them are superconductors at some low temperature. Okay. So I didn't think it would happen. 2 papers appeared in 1 week. Amazingly, both groups, Kinfai and Corey, sent me their paper preprint saying, here is your prediction proven wrong. This is a very complicated problem. There are many variables. Temperature, they all often apply a magnetic field, displacement field, what I call delta in other things. D experiment is called deal. Nu, meaning filling, how much you're filling your band. Theta, the twist angle, the dielectric constant of the background. That's not a variable, but that's kind of unknown, because you're putting HBN on 2 sides. So it's a many-dimensional phase diagram. Okay, so this is one case where theory, if you want to do the full theory, it's going to take longer than what the experiments take, because varying all these things and filling out the phase diagram, 8-dimensional is very, very difficult. So I'm going to show you some. So this is experimental results. The 2 experiments are very consistent. The 2 devices, the main difference is the twist angles are somewhat different, actually quite different. One twist angle is much larger than the other twist angle. And both of them found superconductivity, you can see what it is, of the order of a few hundred millikelvin. Okay, here is the BKT temperature, and other way that is defined half. So it's of the order of a few hundred millikelvin. So the theory, our goal is to do a theory again with no, so what we did here, we took the standard band structure for TMD homobilayer, also developed in Texas. Actually, is developed by originally by Feng-Cheng Wu, Alan McDonald, but Ming Shi, who used to be in Texas, knows these things very well. Or actually, we are dominated by Texas. Ming Shi was in Texas, Jihan Zhu was in Texas. They're both Alan McDonald students. And we use the band structure that everybody accepts as the given band structure. There's some parameters there. If you know what it is, it's redundant. If you don't know, just accept that the band structure is the accepted band structure. That's what we used. And then we said, okay, so what we want to do, we do not know what's going on. We're going to assume there is some boson that is mediating the superconductivity. Okay? Some glue, some bosonic glue that's mediating. What it is, we are agnostic. It could be phonons, it could be something else. But then let's see what coupling constant you need to predict the TC that they're getting. Now, if the two coupling constants are orders of magnitude different, then of course the theory is not very meaningful, okay? So then it's not. So that's what we did, okay? So the band structures are these band structures, okay? These are very famous papers. So continuum band model is this, and there is a term that, as a layer potential because of the applied electric field. And this is what we are trying to reproduce. One is Cornell, one is Columbia. The angles are different. And again, let me emphasize the key physics is the physics of Van Hove singularity. Okay. Again, if you make some kind of continuum approximation, you miss the Van Hove singularity, you are not going to get any superconductivity, which was the key error in my prediction that it would not happen. So what we found, there are many possibilities here. Intralayer, interlayer, intravalley, intervalley. We looked at all of them. Specifically, Jihang Zhu, who is in the audience, looked at all of them very carefully. And we are using some phenomenological bosonic glue, which in my mind, I'm sure are phonons. But I'm not going to say that in public, okay? So it's, so it's, it's some bosons, okay? But then we do the theory. It's the same theory, but now I'm going to show you some equations so that you know that it's really a very serious theory. And you invert this equation and you get a TC. And let me show you the results. So our conclusion is, after comparing all the channels, the highest TC is, the order parameter is S plus F order parameter. So it's not a single singlet. And now comes the punchline. This is sample A, sample B. I think this is Cornell, this is Columbia, or this is Columbia, this is Cornell. I don't remember which one is what, but that's irrelevant. What you notice is the value of G we need to get agreement with their TC. This is, I'm showing you results as a function of G. Of course, as you increase the Bayer coupling, TC is much higher. As you lower it, TC is much lower. But the punchline is both experiments are explained by a G of the order of 100, the coupling of the order of 100 in the relevant units, okay? So we concluded, given that the angles for the two samples are very different, the same mechanism, same boson-mediated mechanism is playing a role. At this point, we still don't know what these bosons are, okay? And here is the order parameter. You can see it's S plus F. We have posted the paper. You should read if you have questions. So the thing is that it's just, interlayer, intravalley coupling. Now, let's see how it compares with phonons. So deformation potential coupling in tungsten diselenide is, DFT calculation gives of the order of 3.2 electron volt. What we need for the two samples are 7.1 and 6.7. It's not very well known. Deformation potential coupling is a very difficult quantity to either calculate or measure. Okay, it's very sensitive because, and even in gallium arsenide, I found out like 35 years ago that the quoted DFT number is off by a factor of 2 because transport is the right way. So it's a factor of 2 disagreement. This is 3.2 is the DFT for bulk tungsten diselenide. We are finding something of the order of 7. It's not an agreement, but I'm not particularly bothered by factor of 2. So what I'm saying, phonons are possible. That's the most I could say. Now, what about interlayer acoustic phonon? They play a minor role here, so they're not very important, okay? So this is for the Rightly mechanism, and then it's S plus F pairing. And this is the phase diagram as a function of applied electric field, displacement field, and filling factor. And as you can see, we have put the experimental point for both. And you can see that it's reasonable, okay? Our experimental point falls where we're getting the maximum TC. So I would say that prima facie, you have to take this theoretical calculation seriously, okay? This is the applied parallel field results. This is unpublished, very recent work. It's actually less than a week old. And basically, these are FFLO pairing. So, the two layers are pairing, and there is a Q vector connecting them. If you take Q to be 0, which will be just the BCS, then when you apply electric magnetic field, the superconducting TC goes to 0 sharply, which is not meaningful. So then Jihang did a full FFLO calculation, and then now there are two variables. You have to also look at the whole TC as a function of Q. This Q is the out of plane Q, coupling the two layers, and then for some Q, TC is maximum. So what I'm showing you here, let's say in this panel, is for this dotted line, the dotted line is Q is equal to 0. So that's, And this one is the maximum TC by varying Q, and over here we are showing you what that Q is, okay, how that Q varies with B. It depends on B also, it's very complicated. And then we do it for, by changing theta, by doing various things. And this is the prediction. And both Corey and Kinfai tell me that they are doing this experiment, applying parallel field. This is a prediction, okay? So we'll see how it works. This is all orbital effect. This is not spin effect because of spin valley locking. If this orbital effect was not there, TC would remain finite for infinite magnetic field. There is no Pauli effect or Croxton limit because this is triplet thing. Okay, it's all coming from FFLO orbital. So the thing is that much of the observed 2D superconductivity, both in Moiré and non-Moiré 2D materials, appears to arise from electron-phonon interaction and Van Hove structure. Van Hove is the most important thing. But the possibility exists that some low TC triplet superconductor arise from isospin fluctuations. We cannot rule that out. But the important thing is that non-S-wave exotic pairing definitely can occur with electron-phonon interaction. So you cannot rule out electron-phonon interaction because it's not S-wave. This is my conclusion, but there's a postscript. Postscript is that we have produced results in reasonable agreement with Longju's talk yesterday, okay? He promised me the paper will show up last night, but the paper did not show up, so you had to just take things from his talk and digitize it, okay? So Yangji just sent me the results like half an hour ago, okay? Because I really wanted to have this, okay? Again, I have not gone through all of it, so please do not ask me too many questions. The idea we already had, that is spin triplet. Long was very gracious in telling me his results some time ago, verbally, not any preprint or anything. It's clear what he's seeing is some kind of spin triplet pairing. And here again, we are using the same philosophy, some bosonic glue. We do not know what it is. And it's a valiant spin polarized superconductor. He gave his talk 24 hours ago. It's a finite momentum pairing. There is some magic D-field region where this happens. And TMD is bad for superconductivity. These are some of his conclusions. These three things qualitatively we explain. Again, I just got these results. So I'm going to just leave this on to titillate all of you and to make the theorists think what is going on. This could change. I have not gone through it yet, but I thought given the great amount of interest in Longju's experiment, I could not kind of avoid showing you these results. And thank you all. I'm going to stop here.
So thanks to Sankar for a very nice talk. Let's move to questions.
There is a difference between twisted graphene and aluminum or lead, and that is that phonons coexist with electron-hole pairs and plasmons in the same energy momentum range. Yeah. So I am not sure that the M-star techniques and so on are applicable to a very narrow band system where...
I would not disagree with you, but let me tell you that whatever is not applicable for electron-phonon interaction is exponentially more inapplicable for plasmons, where there is no Migdal theorem anywhere. So if you say it's not applicable, you should not continue writing papers saying plasmons are giving rise to superconductivity, because it's even more inapplicable there. So what I'm saying is that indeed, that there are various approximations here, and many of these approximations may not be valid here. But if those approximations do not become more valid for plasmons or electron-electron interaction, they become less valid. So the choices are, do nothing, or do the best you can. As a pragmatic person, I take that. But I don't disagree with you. I do agree that, look, the main issue is even more simple, right? To what extent Migdal's theorem applies here, even for electron-phonon interaction, or in all the energy scales are the same. The whole basis of our understanding of superconductivity is, no matter how strong the coupling is, Migdal's theorem tells us that we can just use leading order approximation. And this is, of course, a severe problem, as you know very well. So all I can say is that we are doing the best we can, but your comment is well taken. It's a correct comment, that it's something one should worry about. I'm not disagreeing with you at all.
So, hey, Shankar.
Yeah.
So you set up the beginning of the talk as saying, phonon, there's the default possibility. The other option is, some isospin fluctuation.
Yeah.
So maybe I want to push back on that dichotomy.
I accept your criticism even before we make the criticism. But go ahead.
Right. So the entire set of calculations you're doing is predicated on having a band structure Fermi surface in a normal state. Now, in something like TBLG or TTG, we know that where the superconductivity is strongest, the carrier density is very small. It's not given by the count from neutrality, but by the deviation from mu equals 2. So clearly, the Fermi surface is completely different in the normal state from the one that you're using for your calculations. Even its size is just completely off.
So I totally agree with you, Santhil. Can I rephrase what you're saying in my language? That is that there is huge electron-electron interaction in this renormalization of the basic band structure itself. Huge, including phase transitions and other things, okay? And that is not true, for example, aluminum. Okay, why that's not true for aluminum, we do not know. Aluminum RS is 6, it's very strongly interacting system. It may be true there also, but there is experiment showing that. So, and that our theory doesn't take into account. We are only taking mu star. So it boils down to, and you and I agree, that electron-electron interaction should be included in this theory, non-perturbatively at the same level. And that should be in the bands, that should be in the repulsion. We are just including it approximately the repulsion. It goes back to what Paco was saying also. And those things are not included because I don't know how to include them. Okay, it's a very difficult problem that I can renormalize the band by doing standard renormalization is Z and changing mass, but that's just an equivalent single particle picture, okay? So I have thought about it, and I really have no good idea how to do it, to tell you the truth, okay? So your point is very well taken. So the way my reasoning goes, and this is a more empirical reasoning, we'll do the calculation. Let's see how much of the experimental phenomenology we can describe and explain, and whether we can predict things. And then if it works, we then should ask why aren't those effects very important, okay? And if it doesn't work, we should say those effects are very important. This is not a very compelling logic, but I don't know what else to do. I mean, we have to do something. These guys are writing hundreds of papers, you know, and it's just, I mean, we are supposed to be smart. We have to do something, and I feel totally dumb. Look, I have no, you and I agree, right?
Yeah.
So I briefly saw that your rhombohedral 7-layer, 8 layers, the TC is about 10 Kelvin or something like this, right? So can you just do the calculation for the infinite rhombohedral and then where the TC got the room temperature?
You know, this is something thought about, but we need some clever trick, which I have not come up with. You cannot do it by layer. The calculation becomes more complicated as you go to the layer.
Yeah.
So this is something we are talking. There must be a way of doing the n infinity limit without doing this layer by layer thing, okay?
Right.
Maybe we're going to use large language model and we have all this data. We will have the data up to like 15 and then large language model.
Well, I don't understand. It's infinite layers. Basically, this is 3D crystals, right? So I think that...
you know, if you look at those results, which just came yesterday,
right?
It's really, if you extend it, it's like room temperature TC.
So,
but this is a very good question, which I'm very interested in doing, that we should be able to do the infinite layer without going through layer by layer.
Right.
Okay? If you make a 50-layer sample, it would be stupid for us to, you know, and there must be a way of doing it. Must be. Okay? We are just not clever enough to discover it, but this will come. Okay. Very good point. Okay? Very good point.
So you know, something that's always very striking about all of these theories is that it's superconducting everywhere, right? And then in the experiment, it's only superconducting in little slices. So is the right way to kind of hand-wavingly understand that you know, because you're just thinking about mu star and not thinking about symmetry breaking, this is kind of the background tendency to superconduct, and then the rest has to not get in the way. That's if I wanted to try to square the circle.
If you're my friend, that's how you'll describe
that would be the generous
way. You are
way
my friend,
okay.
Because I'm your friend. But there is another way of describing it. The issues that Paco and Santhil are bringing up, that I agree with, that electron-electron interaction is so non-perturbative here that is changing the basic picture. In which case, what I'm doing is certainly a theory for something, but we don't know what that something is. That something is not what you experiment. I personally think that the regions where you don't superconductivity are where all the symmetry breaking, all those other things taking place is preempting. But I cannot rule out the possibility that, you know, it's all like electron-electron.
Maybe just one follow-up then. So if one did want to remove the repulsion, what's the length scale on which one needs to remove it? Do you need to remove the on-site repulsion, or is screening, screening Coulomb on the scale of a nanometer? mean that then it would really test this.
Yeah, it's really, I think the actual interaction is pretty short-ranged. And you know, it depends to some extent, because you do the static screening calculation fairly honestly, using the bands, it's pretty short-range. I mean, with that we checked, okay? That we checked.
So you mentioned the degeneracy of the S-wave and F-wave pairing. So I wonder if disordering the sample would have any effect on this.
Oh, I'm sure it will. I'm sure it will. In fact, that brings up a question. What is the mobility or mean free path in twisted bilayer graphene? You guys never mentioned that in paper. You know, all gallium arsenide paper, that's the first sentence, what the mobility is, okay?
You say something away from magic angle,
but anywhere, what are the numbers? Is it 10,000, 100,000, 10 million, 1 billion?
100 nanometer,
Yeah, the length scale doesn't help me. I want an energy scale, but anyway, we can talk about it. So what you're asking is a very good question, okay? What disorder does here? Because there is some intrinsic disorder. Even if you do not have external impurities, twist disorder is unavoidable here because of just thermodynamic reason. You know, this is not a stable structure. And what that does is a very important question to all of these. This is in addition to the issue that said, even at one particle level, there are things you are neglecting, okay? And all I can tell you, I expect them to be important, but I do not know how to include them, what to do. I mean, if there was a disorder broadening, I know how to include that. You know, doing a diffusive approximation of the propagator. So it's a very good question, which I agree to be important, but I have no good answer.
So just knowing everything that you know about electron phonon in all these systems, do you have any recommendation? What should we focus on the next 5 years to get to TC 10 Kelvin or 100 Kelvin?
I know I'm extremely bad in this sort of big question thing. I'm an engineer. I like doing calculations. But since you asked, let me put my philosopher's hat on my head. You know, a very interesting question is what Philip asked me. I would love to know how TC evolves as you increase number of layers. You know that there were all these buzzes, right? That graphite may be superconductor room temperature. If you just make the right structure, we know that structure is an important issue because these rhombohedral things are very fragile, right? So I would love to know it's a very difficult experimental question. The second thing is what both Paco and Senthil alluded to, and I'm very interested in it also. What fundamental role is electron-electron interaction playing, even to the picture I'm proposing? Let's say that I'm right, it's mostly electron phonon. But they are both absolutely correct. You cannot just subsume all of electron-electron interaction in a mu star here because it's not aluminum or lead. I mean, how that affect things. What we can do, and we have done in some of these papers, I didn't elaborate it, we do a spin fermion model and include isospin fluctuation also, whenever it's close to a symmetry breaking point, but not inside the ordered state, okay? And we find that the TC is somewhat lower than phonon-induced mechanism, but not zero. So I would love to know, theoretically is what I would like to know, and if we have a theory, we can tell you what experiment to do. These are the two important questions. Actually, TC of the infinite system is not an important theoretical question. It's an important practical question. Including electron-electron interaction on the same footing as electron-phonon interaction is a more important theoretical question, which, again, I would like to know. Okay.
So given that you have a quarter metal, right?
Yeah.
And if you have a superconductor, it's going to be P plus IP.
Yeah, it doesn't have to be pi. It could be F also. It could be something higher, but at least P plus IP. Right. Yeah.
And so what do we learn more by doing this calculation?
Oh, I do not know. I don't think we learned much from any calculation. The experiment tells us everything. So I do not quite know. Now we are getting into ontology.
Right. So yeah. in the question of repulsive interaction.
Yes.
This was after 24 hours after the experiment,
yeah.
But way back in 2017, we looked at what happens if you consider superconductivity. If you ask what happens with the repulsive interaction in a single species of fermion around K and K prime.
Yes.
This was in the context of hold of TMD.
Right. Mm-hmm.
But we found that with the RG calculation, you predict one of the possibilities. If you do intra-valley, it is like this, right? Because it's the same situation.
Yeah.
We've also done DMRG simulation, and we also found pair density wave. Right?
She did 2D DMRG?
Yeah, well, just, DMRG is always fuzzy one. So these were ways of getting
So, now I understand what you're asking. Yeah, now I understand what you're asking. So let me comment on that. I would not comment on your work because I don't know it. I have done many RG calculations on it. I don't even list it. RG here is completely useless as far as I'm concerned. RG gives you 500 phases. Every phase anybody could think of, any phase people could not think of. All of them show up at t is equal to 0. Very fragile, they're competing with each other. In fact, your student Sue did some of this. I did Robert Throckmorton, a 32 parameter RG. I concluded RG is not going to solve this problem. RG method. So I think TC, one has to talk about TC if you want to. What happened at 0 temperature is a matter of profound inconsequence to the real world. Because in 0 temperature, all metals are converted into superconductor. But we do not take that into account. So one should be careful in asking theoretical questions. It's a matter of taste. I'm not interested in ultimate theoretical truth. I'm much more interested in what can be seen in the lab. So I think what RG is telling us is just what is possible, not what happens. And we are trying to calculate what happens. Unfortunately, for that, you need a model. Okay. Yeah. No,